Hey there, and welcome. Today, we're going to be detectives, but our crime scene, it's the entire universe. And our main piece of evidence? Just a single beam of light. You see, hidden inside that light, there's a secret code, an atomic fingerprint that tells us exactly what distant stars are made of. It reveals the beautiful, hidden architecture of matter itself. And our investigation starts with something you've definitely seen before, but maybe never looked at this closely.
Right, we all know this one. You take some white light, like plain old sunlight, you shine it through a prism, and out comes a beautiful continuous rainbow. We call this a continuous spectrum. It's just a seamless blend of every color from red all the way to violet, with absolutely no gaps. The red light, which has a longer wavelength, bends the least, while the violet light, with its shorter wavelength, bends the most. Pretty straightforward. This is our baseline. This is what we expect to happen.
But this is where the mystery really begins. What if you take a gas, like hydrogen, and you zap it with electricity to make it glow? Well, the light it gives off looks completely different when you put it through a prism. Instead of that full rainbow, you get just a few sharp, brilliant lines of color. And they're separated by these big, empty black gaps. So why? Why aren't all the other colors there? What on earth does this weird barcode of light actually mean?
Well, it turns out the answer isn't really about the light itself. It's about the atom that's emitting the light. To solve this whole thing, we need to dive deep inside the atom and look at the strange, specific rules that its electrons have to follow.
To really get this, we have to wrap our heads around a crucial concept: quantization. Now, think of it like this. An electron's energy isn't like a smooth ramp it can just slide up and down on. No, it's more like a ladder. An electron can be on the first rung, or the second, or the third, but it can never be floating in between the rungs. It's just a fundamental, kind of weird rule of the quantum world. Energy comes in these discrete, specific packets.
So this energy ladder, it works in two directions. An electron can absorb a very precise packet of energy to jump up to a higher rung on the ladder. But that higher state, it's unstable. So when the electron inevitably falls back down, it has to release that extra energy. And it does that by spitting out a single particle of light, which we call a photon. The bigger the fall, the more energy the photon has, and that's what determines its exact color. Okay, so this whole quantized behavior of electrons, this jumping up and falling down the energy ladder, it actually gives us two different ways to see an atom's unique signature. They're like two sides of the very same coin.
Let's break it down. On the one hand, you've got emission, which you see up top. That's where we energize a gas, forcing its electrons to jump up and fall down, and we just capture the specific colors of light they give off. On the other hand, you have absorption on the bottom. Here we do the opposite. We shine a full rainbow through a cool gas, and we see which specific colors get snatched up or absorbed by the electrons to make their jumps, leaving these dark gaps in the rainbow.
And this is the brilliant part. The bright colored lines you see in the emission spectrum, they perfectly match up with the dark, empty gaps in the absorption spectrum for the exact same element. It's a perfect match, a photographic negative, you could say. The colors an atom likes to emit are precisely the same colors it likes to absorb, and that's because both spectra are created by the exact same set of energy rungs on that atom's unique ladder.
So, to crack this code, scientists knew they had to start with the simplest atom there is, hydrogen. With just one proton and one electron, its spectrum was like the Rosetta Stone. It was the key that allowed us to finally translate these mysterious lines of light into the language of physics.
Now, back in the late 1800s, a physicist named Johannes Rydberg discovered something absolutely incredible. A pretty simple mathematical formula that could predict the exact position of every single line in hydrogen's spectrum. Let's break it down real quick. That symbol on the left stands for wave number. It's just a convenient way to measure the light's color, and it's directly tied to its wavelength. That big number is the Rydberg constant. But the real magic is in N1 and N2. These are just whole numbers that represent the energy rungs the electron is jumping between.
Okay, let's actually make this real. See that bright red line in hydrogen spectrum? That happens when an electron falls from the third energy level down to the second. So we just plug those numbers in. N1 is 2 and N2 is 3. We get 1 over 2 squared, which is 1/4, minus 1 over 3 squared, which is 1/9. You do the math, multiply by that Rydberg constant, and the number you get corresponds exactly to a wavelength of 656 nanometers. It's a perfect prediction.
And this amazing formula revealed something else, that these lines come in entire series or families. The final landing spot for the electron, that N1 value,
is what determines which part of the spectrum the light shows up in. For example, if the electron drops all the way down to the first level, n1 equals 1, it releases a really high-energy photon we can't see, in the ultraviolet. That's the Lyman series. If it only drops to the third level, n1 equals 3, it's a lower-energy, infrared photon in the Paschen series.
The only series that produces light we can actually see with our own eyes is called the Balmer series, and that's where electrons fall down to the second energy level, so n1 equals 2. That red line we just calculated, that's a drop from level 3 to 2. The greenish-blue line is from 4 to 2. The next blue one is from 5 to 2, and so on. Each visible color is a direct map of a specific electron making a specific drop.
So here's the crucial point. This isn't just some neat physics trick that only works for hydrogen. This principle applies to every element in the universe, and it gives us an astonishingly powerful tool to work with. Because every single element, helium, carbon, iron, you name it, has its own unique number of electrons and its own unique set of energy rungs. Each one produces a completely unique line spectrum. Just like a human fingerprint, this spectral pattern is an unmistakable, one-of-a-kind identifier for that specific element.
And this technique just became this powerful engine for discovery. By analyzing the light coming from different things, scientists could identify elements they already knew about, and even find brand new ones. And the most incredible example of all is helium. Astronomers saw its unique fingerprint in the light from the sun decades before it was ever found here on Earth. Think about that. We discovered a new element simply by decoding starlight.
So, what started as a simple mystery about some gaps in a rainbow ended up revealing something truly profound. The light that an atom emits is a direct reflection of its internal architecture. The fact that these lines are so sharp, so predictable, and so regular proves that atoms aren't just chaotic misses. No, they are highly organized, elegant structures, all governed by the strange rules of quantum mechanics.
All right, let's pull it all together. What are the key things to remember from our cosmic detective work?
First, we've got the Rydberg formula. This was the mathematical key that unlocked the hidden order inside the atom. It allowed us to translate those electron jumps into specific, predictable colors of light.
And our 4 main takeaways. Number 1, electron energy is quantized. It's a ladder, not a ramp. 2, light is either emitted or absorbed when electrons make those jumps between rungs. 3, and this is the big one, because every element's energy ladder is different, each one has a unique spectral fingerprint. And finally, that means we can use these fingerprints to analyze the light from distant stars and know exactly what the universe is made of.
It's amazing, right? It all started with a simple prism and a weird observation, and it led to a deep understanding of the atom and of the stars. It really makes you wonder, what other secrets are being carried by the light that fills our world every day, just waiting for us to find the right way to look? Thanks for joining me.